what am I presenting tonight? Well, this really interesting story of a new deposit type, really, and a really interesting minerals association of rutile and graphite, probably never heard of before, in Malawi. So let's get into it. And really the talk is kind of a bit of the discovery story, and the geology, really, and a few other technical tidbits around metallurgy and these sort of things, and sort of finishing off with a bit of an exploration model. I'm not giving away all of our IP at this stage, but some of it I will. So consider yourselves lucky for the bits I'm giving. But let's kind of get going. So what is it? It's the largest natural rutile deposit in the world now, and really found over the last 3 or 4 years in Malawi. And at the same time, it's the second largest flake graphite deposit in the world. Really, the deposit in itself, or in its sort of own right, is kind of its own province, because it's 200 square kilometres, so probably bigger than most other mineral deposits in the world in terms of its aerial footprint. And maybe bauxite and maybe some other mineral sands deposits might be, you know, possibly reaching the hundreds of square kilometres of aerial extent, but not many. So it's unconventional mineralization style for heavy mineral sand, or heavy minerals, really, and it's residual, otherwise known as an alluvial deposit, not to be confused with placer deposits or alluvial deposits. So kind of think bauxite, the exception being the material is completely unconsolidated. It's a grassroots discovery established from scientific first principles. So where are we? We're in Malawi, which is known as the warm heart of Africa, near the east coast of Africa, but landlocked, really down the Rift Valley, Mozambique to the east, Zambia to the west, and Tanzania to the north. A few other projects in Malawi. Kalakera, most of you may know of historically, on care and maintenance at the moment. Uranium project I found back in the day, Kanyika niobium project, so a couple of rare earths projects around, and one that's seeing a lot of press these days and having a lot of success, Lindian at Kangankundi on their rare earth carbonatite deposit there. So regional geology. So Malawi is dominated by orogenic terrains that sit between the Archean, Zim, Kasai and Tanzania cratons. It's seen a high-grade orogeny at around 1 billion years ago, and then that is overprinted. That has been overprinted by the Pan-African orogeny when all of those bits of Africa came together. A number of rutile deposits and occurrences and graphite deposits are known across East Africa in similar rocks to this. However, the rutile deposit, has previously only been known in placers and never in this setting before, never in this alluvial setting before. So here we are in central Malawi, in the South Iramai domain, which is comprised of 3 subdomains. Each contains ortho and paragneises. The Lilongwe subdomain where we are located is dominated by paragneises that contain graphite and rutile. So I really want to start this with the discovery story. We started in Malawi, and Matt Wheeler, who is sitting over here to my right, was part of this process as well. We went into Malawi looking for graphite in around 2010, and in 2011 we pegged about 8,000 square kilometres for graphite. We used a number of data sets to put a bit of a story together at that time historical exploration in the 30s, 60s, 70s, 80s and 90s. And also we're able to put together some data from waterbore drilling in this area of highly weathered terrain that showed graphite occurring in these areas where there was no outcrop as well. So we identified dozens of prospects cropping out in where rocks were exposed to the east, and that is the area in the grey over this side, and the areas that are weathered are in the yellow to the west. So we identified many or numerous sort of graphite occurrences in waterbore drill hole logging, historical waterbore drill hole logging. We put all that together. This is kind of the early story we came up with on graphite specifically. That graphite did occur, substantial graphite did occur in this area that was highly weathered to the east of these exposed rocks. Let's move on there. So after numerous years of exploration, sort of 3 or 4 years of exploration, we discovered 2 discrete or distinct graphite deposit styles. Fresh rock, when one of these is the Dewey deposit occurring here to the east of the capital city of Lilongwe, and then also these weathered or regolith hosted deposits, and a key deposit that was discovered and worked up to a PFS stage is this Malawi deposit to the south of Lilongwe. And that was discovered in about 2016 and taken up to the PFS stage in about 2018. These, a characteristic of these deposits is they're coarse flake, high purity graphite and highly crystalline graphite. So really what was that telling us? Not that it was telling us this, but this is because of granulite facies metamorphism, so quite high grade metamorphism, coarse crystalline graphite. So where did this rutile come from? How did this story develop? How did this morph into finding the world's largest rutile deposit? Well, we actually discovered rutile as an accessory mineral in these graphite deposits back in 2013. And in this slide, sorry, faux pas there, no scale on the slide, but it's about 1 millimetre across. So you can see that rutile grain there is probably in excess of 1 millimetre, and it's in equilibrium there with coarse flake and a thick book or thick flake of graphite. So intimately associated rutile and graphite. At the time, we had no idea of the importance of rutile. It was an interesting accessory mineral, and we didn't really pay too much attention to it other than that. So then what happened? Well, what happened was we were doing this test work on these graphite deposits, metallurgical test work, and I started seeing these assays. Actually, the assays were for environmental purposes, what's going into your tails dam, etc. I started seeing these high titanium assays coming through from these tailings. It's like, well, interesting, but whatever. But thought, what if I just connected it back to that rutile that I'd seen? So what if that is rutile, or the majority of it is rutile? What if we could recover it, etc., etc.? So we actually took a sample of the tails post graphite processing. So graphite had been floated out of it, and we're left with this sand tails. I took it to AML down here in Osborne Park, and I asked if you've ever done any mineral sands work. You might know Jacob, one of the key metallurgists down there. I asked him to put it over the table and see what he could do with it, and he was able to make a high-grade rutile product out of it. So this is out of material that was from this is regolith, unconsolidated, ferruginous peelith, mottled zone material, and saprolite, and he was able to make a high-grade graphite, rutile concentrate out of it, and very high spec concentrate as well. So We confirmed this rutile graphite association in 2018. So this work was done on those initial graphite deposits. We found that higher rutile grades were not generally associated with higher graphite grades, particularly in the near surface area. So it was a bit cryptic at that stage, this mineral association. There was an association, but it was a little bit cryptic in this surface, in this surface zones in the regolith. However, the presence of any graphite at all appeared to indicate the likelihood of rutile occurring. So we worked out this well-developed weathering profile, had concentrated rutile in the upper 5 to 10 metre parts of the weathering profile, particularly in the soil, ferruginous pedolith down to about 4 metres. So this is ferruginous material, but it hasn't got so much iron in it that it has become lateritic jury crust. So it's this fluffy ferruginous material, uncemented, and then also in the modelled zone below that. And we found this rutile product could be produced from this material. So we came up with this hypothesis at the time that it was possible, it could be possible, or was it possible that large or very large regolith-hosted alluvial deposits could occur across the Lilongwe Plain. This is this weathered area out to the east of the capital city of Lilongwe, associated with graphite mineralization. At the time, we did come to the realization that you didn't need high-grade graphite or low-grade graphite. You just needed graphite presence that was indicating this rock or this protolith that contained rutile mineralization. So once we realised that and came up with this hypothesis, what did we do? So we went back to a lot of our regional graphite drilling in this weathered terrain, again, east of the city of Lilongwe, the area known as the Lilongwe Plain. Assayed a bunch of selected historical graphite drill holes just for TiO2 then at that stage, and then looked at the mineralogy of the TiO2 species. We found numerous areas of 2 to 3% TiO2. That's not all rutile, by the way, but of TiO2 in these historic drill holes that were drilled for graphite across this sort of very large area. After a bit of work, we determined in many areas that rutile was the dominant TiO2 mineral, and it was highly crystalline and clean rutile grains and easily liberated. So we didn't have any of these composite grains or anything like that, and sitting in a sort of sandy, clayey matrix. So overall, in the areas of higher grade, we were able to get recovered grades in the sand fraction of around 1 to 2% natural rutile. We found that rutile was particularly enriched in the near surface area, on average about the top 4 metres of the profile. So that's this ferruginous pedolith zone that's seen really significant volume loss during that weathering profile. And then the rutile is just sort of packed down in place and mushroomed out a little bit. So the discovery of Kasiya, now the biggest rutile deposit in the world, was achieved through our understanding of how the rutile occurred from our graphite work, desktop work evaluating all of the historical bulletins, geology bulletins and maps, geophysics. Then we understood that rutile concentrated in the near surface, so soil sampling was an obvious way to go. Mineralogy, making sure we were looking at rutile, not at other titanium minerals like ilmenite, etc. Then we went to a very low-cost drilling method, hand-auger drilling, which enabled us to cover a lot of ground very quickly. We set up our own in-country laboratory because we were getting like 16, 20, 24-week turnarounds on samples, sending them back to Perth or South Africa, etc. So we found that it was, we made a decision to set up our own laboratory in-country. And that was one of the smartest decisions we ever made, because in the end, we were getting a 5-day turnaround from drilling a hole to getting an assay, essentially. And then we refined the exploration model after that. So I spoke about sampling, soil sampling. We worked out that this material was concentrating near surface and in particular in the soil. We really just started driving these regional roads, jumping out every 400 or 800 metres, walking into the field, 10 metres, taking a soil sample, bringing it back, taking it back to the lab that we had set up in Lilongwe, processing it and coming up with a number and working out whether we wanted to continue in that area or move off and look for some other areas. What we found then was, numerous, I guess, very high grade rutile soil anomalies. For context, if you're not that familiar with rutile, probably anything over 1% would be considered high grade. Sierra Rutile's reserve is 1.4%. We have areas in these deposits between 2 and 3% near surface. The overall grade is about 1%, but it's huge tonnage. But there are some higher grades of 2-3% near surface. So we found this anomaly at Kasiya and a number of other anomalies called Railroad West and Railroad. Railroad West and Railroad were our first targets that we drilled. That didn't come up. That's exploration though. Wouldn't be exploration geologist if you hadn't had a failure or drilled a dud. But then, yes, so this Kasiya anomaly was about 2.4 kilometres wide, unknown strike length at the time. And that anomaly is a very, very, very tiny bit of what ended up being the entire deposit. It actually ended up being a tiny little limb off the southern end of the deposit, the southwestern edge of the deposit. So the soil anomaly was over 2% rutile, over about 2.4 kilometres. In the field, one thing that we did notice as well was this really obvious coarse kyanite lag. So that became a sort of indicator mineral for us. Once we'd sort of worked that out, we went back to these old geological maps and we'd realised, and that you'll remember these maps, but the old British and Nyasaland, as it was called those days, Geological Survey, geos had mapped areas of kyanite lag and put them on the maps. So we realised that we digitised all of those areas and they became our primary targets for lines of soils and then handled the drilling. So this handled the drilling, simple, pretty good confidence, and is able to get you to an inferred resource. Other drilling we use is push tube, which is just you might be familiar with the banker drilling they do in Indonesia on the nickel laterites, but it's essentially just bashing a tube down the hole, pulling up every 1 metre, pulling the core out, but we're getting perfect core. If you use water to drill or standard diamond drilling, you get a lot of core loss. So that was as a very, very effective method, and obviously air core drilling to get us some deeper holes. Some photos of some early hand auger drilling here, probably around the time of discovery. And then, here's our first discovery cross-section. So wide space hand auger drilling. Well, what we thought was wide space at the time was 200 metres spaced along the line. Funnily enough, we ended up going to about 4 kilometres by 800 metre spacing. We actually had to expand our drill spacing and not bring it in for this discovery. So that was a quite, I've never had to do that before, I don't think. So here is some of the initial hand auger. This is when we knew we were really onto something. So 7 metres at 1.3%, 8 at 1.2%, 13 at 1.1%, etc. With these higher grade zones in the surface, 3 at 1.8, 5 at 1.3, 3 at 1.2, 4 at 1.5, etc. Those are all from surface. These end up being nowhere near our best drill results, but we were very, very excited to get them. So we knew we were onto something, didn't know what we were onto, but we knew we were onto something. So then by 2020, we had identified an area of 66 square kilometres of drilled mineralisation. Okay, not quite resource, but of drilled mineralisation. Most holes were 1% plus over about 10 to 14 meters. And this is all that hand auger drilling. So we were getting, we were not able to penetrate much below the water table with this drilling. And most holes were terminating sort of 10 to 14 meters because of excess water, and the sample would just slip out of the spiral there. So these are some of the better results as at that time, you know, we started expanding this discovery. I won't read them all out, but a few 11 meters at 1.7, including 3 at 2, 7 at 1.7, including 6 at 1.8, 11 at 1.2, including 4 at 1.72. All of those includings, all of those high grade zones are from surface. So this high grade rutile is right at surface, right under your feet. So to date, what have we done? We've completed about 27,000 meters of drilling over about 200 square kilometers. We've obviously infilled areas of higher grade to indicated. Sorry, there's no scale. It's a faux pas there. No scale that you can see on that, but that's about 25 k's north south and about 15 kilometers east west. In terms of the local geology, so it's underlain by this pretty nondescript paragneiss. Low-grade graphite in it, lowish grade rutile, maybe 0.4, 0.5% rutile, maybe 2% graphite on average. We call this unit PGRG. The trend of the rocks is the trend of the regolith hosted mineralization obviously follows the trend of the basement rocks, being north-south to northeast, southwest varying. The weathering profile includes concentrations of iron oxides and hydroxides in these near surface ferruginous peatolith zones and the mottled zone below that. Here's some very quite recent geological interpretation. This is by this project called GEMMAP, which was a project, a remapping project of Malawi by the BRGM and other groups, and this mapping was actually produced after the discovery, but it shows that the resource occurs exclusively over the top of this single unit, which actually doesn't even have a name. It's called, I can't even read it, but the PRGM has just given it a letter and numerical name. But really, what is this unit? It's a package of paraneises that are granulite facies, obviously, that contain, as I said, sort of 1 to 2% graphite, about 0.5% rutile in the fresh rock, and really sort of pretty nondescript rock when you look at it. But it is the source for this surface mineralization that's developed over the top of it. So let's start looking at a bit more geology. This is a eluvial placer or eluvial deposit, otherwise known as a residual placer. High-grade rutile occurs near surface, formed by weathering of the primary host rock and concentration essentially in place, essentially over the top of that mineralizing paraneiss unit, but it also mushrooms out at surface. I'll show you a few cross sections later. So you get this sort of packing down of rutile in place. And in fact, what happens in that weathering process is you get volume loss, particularly in the top 10, 20 meters. The graphite is sort of broken down a bit and depleted because graphite's light, so depleted by wind and water. And the graphite obviously gets broken in that, it's quite brittle, gets broken in that physical deflation process. Rutile being unreactive in this environment and heavy, just seems to pack down in place in that sort of top 3 or 4 or 5 meters. And you get that real enrichment there. Again, important associated mineral, kyanite. Kyanite is associated with rutile. Kyanite's a heavy mineral and it's resistant and very coarse. Just have a bit more of a look at the source rock. Obviously, it's paragneiss, aluminous in nature, but containing kyanite. Presence of carbon, obviously, in terms of producing, having that graphite. Obviously, has some titanium in it. That was probably flushed into the system in higher energy times. So protolith clearly of sedimentary origin. Then, looking at the mineral assemblage, and it's really simple, right? When you look at these very, very basic metamorphic phase diagrams, we have to be in the kyanite. We know we're in the kyanite stability field, obviously. Everyone remembers that from first year metamorphic petrology, I think, or maybe it was second year, I can't remember. But graphite obviously occurring in equilibrium with rutile as well, and with kyanite, puts us right in that very, very top of the granulite facies there, above that rutile stability line. So we know we're in pretty high grade rocks here. And kyanite and graphite, very, very good indicators in this case for rutile. What does this material look like in core? Well, the ferruginous pedolith, there are some gravelly parts, but nothing cemented at all. So I've crossed out that auritic jury crust, and I've crossed out cemented here. There is some loose gravels, but really this zone's ferruginous pedolith in the top 3 or 4 meters, getting these rutile grades of around 2%. Then typical model zone rutile grades, typically probably around 1.5%, and then saprolite proper down in here, rutile grades, somewhere between 0.7 and 1%, but a lot of volume down in this area as well. Graphite grades are higher as you get further down the profile, and graphite averages something like 1.5% or so across the whole deposit. So I spoke about it before, but one of the key, I guess, factors in allowing us to discover and delineate this deposit so quickly was that we worked out that we had to set up our own lab. We were getting, as I said, 12, 16, up to 24-week turnaround, because it's quite a complex process. We're really having to solve, because the heavy mineral content sort of varies in these weathered materials, we're not able to use a traditional mineral sands method by getting the total heavy mineral content and then multiplying it by some mineralogical factors. What we had to do, each sample itself is solved for recoverable rutile, right? So we're essentially making a rutile con, actually in this case, a non-magnetic concentrate in the sand fraction that contains the majority of rutile for every sample here. So it's pretty involved. Setting up this lab really helped us. And as I said, in the end, we're getting about 5-day turnaround from drilling the hole. So not only really significant turnaround time benefits, volume benefits in the number of samples we can put through as well, but we also providing a lot of employment there. And at busy times, we've got about 50 employees working there in Malawi. And this is an exploration program. This is not a mine yet. And a lot of training going on there as well. So what is this is a very early prototype version of our laboratory. You see the photos here. We actually had the wet table outside and we didn't have a cover on it. So when it rained heavily, it was a little bit of a problem. But other than that, it is a wet table, so it's designed to be in a wet environment. But so we had set up this heavy minerals lab in Malawi. First stage is desliming. So we had a number of sinks, and we had techs desliming the samples by hand. The wet table, obviously, you see here, producing a heavy mineral con. And then to make sure we separated out the other junk titanium minerals from the rutile at magnetic separation stage, then a weighing, and our XRF on the non-magnetic fraction. And that's just a very, very, very basic flow sheet. Obviously, it's a lot more complicated than that, and there's a lot more drying and weighing stages throughout that. But this allows us to get real-time semi-quantitative rutile results within 5 days. The only part of this that's not quantitative is the XRF. The rest is quantitative, and we've had our competent person come to site numerous times and vet and verify all of our work that we do there. So really what we do now is just send off a non-magnetic concentrate that we know the weight of. We send that to one of our Perth labs for a quantitative XRF, and that's our process. A few more photos. This is when the lab was upgraded. We moved into a bigger warehouse. We now have a 80 sample a day capacity, which is quite a lot of drilling. That's 8 10-meter drill holes, if you like. We've brought our own carb code magnetic separator, so we do the mag sep on site now as well. And again, providing a lot of training and employment opportunities there for Malawian employees. So now the resource. So we started, our first resource was in December 2021. It was about 600 million tonnes at about 1% rutile and about 1.3% graphite. And this sort of depiction is the resource area at that time. I think I read the scale there. So 10 Ks. So yeah, oh, there we go. So 30 Ks long and about 15 Ks wide is the identified mineralized area at the time. That was the drilled mineralized area, but only enough drill density to sort of do a resource estimate on, I think it was 66 square kilometres. So that was about 600 million tonnes at 1% rutile. Then we moved to now, when we have 1.8 billion tonnes at 1% rutile and about 1.5% graphite. 1.2 billion tonnes of that is indicated in the blue and the rest is inferred in the red. An interesting point as well, not that it's part of the technical conversation, but got a rail line actually running over the deposit, operating rail line running over the deposit. So that was that's quite a bonus. Okay, the resource, we can see the high grade areas and indicated areas in the hotter colours, but total of 1.8 billion tonnes, containing about 18 million tonnes of rutile and about 24 million tonnes of graphite, which makes it the largest natural rutile deposit in the world by about 2.5 times the size of Sierra rutile, and the second largest flake graphite deposit in the world, actually behind only Syrah Resources next door in Mozambique. Okay, couple of cross sections of the resource. Rutile, and actually these are old pit shapes, but don't worry about that. They've been updated. We can see all these hot colours in the top 3 or 4 metres, the very high grades of rutile lag up there, and then lower grades in the mottled zone and saprolite proper. And then, so that's coloured by rutile. That top section, this is a different section, but this is coloured by graphite. We'll see how depleted it can be, or it is at surface, but then how the graphite grades really pick up at depth. Interestingly, in this recent program of sort of mainly infill drilling, we've actually jagged some much higher grade graphite areas as well. So it appears that the one hole from memory was 14 metres at 14% graphite. So there are that, notwithstanding the overall grade is about 1.5% graphite, there are some high grade graphite areas, and it's all hosted in this soft saprolite. None of these drill holes are all air core. These deeper holes are all air core. They all terminate on saprolite. All of this material is basically friable saprolite. So at the moment, we are working on a PFS. We did complete a scoping study last year. So we've selected hydro mining or hydraulic mining for this project, which uses high pressure water powered by electric pumps. The advantage of that is you can power your mining equipment with renewable energy. Now, the grid in Malawi is actually hydro, so hydro dams powering hydro mining here, and we'll also have a solar plant and a small diesel backup plant on site. And quite a low-cost mining rate for this unconsolidated material. In terms of processing, what do we do? Okay, so deslime and remove oversize. So we use 45 micron, and then HMC, traditional mineral sands flow sheet, really. So deslime in a cyclone, gravity separation for the sand fraction to make it HMC. During that gravity stage, we actually make a light mineral concentrate as well, or we take the lights fraction of the tails from that. That lights fraction contains all the graphite. That gets shoved off to a graphite flotation plant. The heavies continue going through a traditional heavy mineral sands dry plant, where we have electrostatic separation, magnetic separation, and then making your final rutile product. Graphite, obviously, that sort of semi-enriched graphite sand goes to flotation, so rougher float, cleaner float, polishing and attritioning mills, thickening, filtering, drying, sizing and bagging. So really, what is it? It's two traditional flow sheets bolted together, really. So pretty simple, not a difficult concept to understand. Quite lucky with that material. We did a lot of metallurgical test work early on because we recognised this material was a bit different from traditional sands, and we had two quite different products hosted in the same material. So we've got some pretty good metallurgical performance out of this stuff. It's because we have coarse, highly crystalline rutile, coarse, highly crystalline graphite flakes, simple mineralogy with very little difficult to separate or near density gangue minerals, really high spec products at 96% TiO2 for the rutile, very good grain size for the main industrial uses being pigment, welding and titanium metal, and really low impurities, I guess. Just a picture showing you, this is a wet table, not a spiral, obviously, but easier to show on a wet table, how the graphite and rutile streams separate with gravity. Obviously the heavy's stuck over here, but then the graphite coming right over here into this quite specific cut. So as you can see, quite easy for us and simple to make this graphite light minerals cut. Premium spec graphite as well, coarse flake, high purity, so should be suitable for all applications, and in particular, the battery anode application. Now, after all of that, we've got something, pretty different here that we probably haven't seen. Well, we haven't seen before, at least not in an economic sense. Maybe a few notes in academic texts about this sort of mineralization, but nothing has ever been found to be economic, and nothing of this size, that's for sure. So what do we need here? I've developed this very, very, very basic model, but Proterozoic basin, periods of algal growth and influx, probably some higher energy periods to bring those titanium-rich sediments into it. High-grade orogenesis, Precambrian shield assembly, and in that high-grade regional metamorphism to at least granulite facies, so we get into that rutile stability field. Second part of it is I've got a slide out of order there. Anyway, weathering in the tertiary. So this deep, prolonged weathering period in the tertiary, where we get that volume loss and deflation, the packing down of the rutile. All of the silicates, or the majority of the silicates, are set quartz, obviously, altered to clays. And the resistate minerals, including kyanite and rutile, concentrating in the surface. One final and very important point, you need the entire profile to be preserved. If you have any significant weathering, any significant erosion, I should say, you lose that enriched surface layer of 3 or 4 meters. And we do see that locally in places, but for the vast majority of the area, we have the entire weathering profile preserved. So very, very important there. I have to go back here. So then what to do if we're exploring for this type of deposit, or if you want to go looking for this? So Proterozoic paranesis must be at least granulate facies. Graphite and kyanite are key indicator minerals, and you must be in the kyanite stability field, obviously. Graphite, a good indicator mineral, but also beware of iron sulfides, particularly if you're using EM. Plenty of iron sulfides sent us on a loop here. I didn't talk about that, but they did. Must have a very large area of near surface mineralizing rock unit from either structural thickening or from shallow dips. If you have tram track geology, you're probably not going to have enough area to find a deposit of this size or potentially of economic size, so be careful of that. I spoke about the preserved weathering profile, and you can't have significant lateritic jury crust, so it needs to be probably iron poor rocks, and you also can't be silcreted or cemented with other cement products that silcrete in particular, maybe calcrete. Doubt you get it in these sort of environments. And I think that's the end. Just some acknowledgements. Obviously, Malawi government and specifically Ministry of Mines Geological Survey, the GenMat group that has done a lot of new geology, geophysics, etc. in Malawi over the last 10 years or so, which includes the BRGM, GTK and CGS out of South Africa. And for my senior technical team, Dries Kruger, Sam Moyle, Paul Marcos, Reed, Will Narenda, Sam Mahango and Tupochi Makaleni. They've all been integral, long-term employees and integral to the discovery of this really new style of deposit produced from scientific first principles, really. And that is the end of the